This is 3-Eye Atlas, as imaged on the 9th of November. Yes, it finally has, as we expected, tails, enormous tails. But there's a bit of a problem with these tails. They seem like they're too big for the time from which it first brightened up to produce these tails. The perihelion pass that it made on the sun on the 9th of on the 29th of October. So let's look at this real quick. The main tail pointing away from the sun is back here. And interestingly, there is a huge powder puff of something at the initiation of that tail, whatever it was, explosive event or the thing breaking apart or firing thrusters, as Ovilo might suggest. And you can see a couple of anti-tails in both of these images pointing as it is toward the sun. Now, here's the oddball thing about these tails. These anti-tails are 0.9 million kilometers in length toward the sun against the solar wind, which is traveling about 400 kilometers per second, whereas the material from these tails should be only traveling 0.4 kilometers per second. So they are fighting, swimming upstream, more or less. We'll go all into that a little bit, but the interesting thing is this tailback. Now that is also 620,000 miles. So facing the sun. Now these tails on the outside, these suckers are 2.85 million kilometers, or about 1,860,000 miles, 1,860,000 miles. So those are large, ginormous tails. So here's the average speed. The average speed of materials coming off of a comet, and it's pretty much the good measure speed, is 0.4 kilometers per second. So how do these tails get to be so big? Because if you go through the math of that, and you figure what we had from the time that it was first saw to brighten by GOES 19, SOHO, and Stereo A, which was on the 29th of October. The 29th of October. There's only been through the night from there to the 9 November, there's only been 11 days pass. So if you do the math and you divide 0.4 kilometers per second into 285 million kilometers, for example, for this long tail back here, what you get is you get 7,125,000 seconds, or 118,750 minutes, or 82.45877 days. Well, the decimals are, you can ignore most of that. But anyway, almost 2 months. It should have taken almost 2 months, 80 something days. So let's talk about this a minute. We're going to talk about this and some other aspects of this strange beast, which just won't turn us loose. How in the world do you get a tail so much longer than it ought to be? Now, some particles might travel up to a meter per second, some of the light gas molecules, but they still should be about a month to make that length. It shouldn't be that long. So that is interesting. Does that suggest a technological thruster? Oh my gosh, guys, this stupid comet, whatever it is kind of like, a bad Saturday night date. She committed so many antics, you just want to forget it, and it pulls up in your driveway Monday or Tuesday morning, blowing its horn and acting up, and if you ignore her, she blows up. Well, you just want to forget it, right? Well, I don't let you. But you know what? Just like that, this comet, whatever it is, came around blowing its horn. You had to actually send out a signal. And a lot of people made a lot of hay about that signal, but it's just a typical signal you'd expect from the OH molecules in the cloud when they get excited by sunlight. Nothing to write home about there, my friends. So we're not going to dwell on the signal from the comet. Oh, there's blowing its horn. But the blowing up part, that might have happened. It may have just exploded. That could be what happened to that powder puff. And it could explain on some of these things. But still, there's still some questions here. So we'll get all into this. And we're going to have to look, we're going to just consider what Avi Loeb had to say about this strange object. You know, he's done a lot of math on it himself. That was my math coming up with how long it should have taken to create those tails that long, given the typical speeds of cometary dispersion. Okay, so Avi points out a couple possibilities. His first possibility is that the jets are naturally produced out of the ice on the surface of the rock, through sublimation. Now, bear in mind, sublimation is that process, so you'll understand what it is. You ever put ice in your freezer and come back and not touch it and come back a month or two later and notice there's not as much ice there as there was, that it's kind of like evaporated? Well, that's sublimation. That is the material off the surface of the ice sublimating into the atmosphere of your freezer. Now, in space, liquid is unstable, so things go from solid to gas, and that's sublimation. So when you shine light on ice in space, it don't melt into a liquid, it just goes straight into gas. And that is your sublimation process. But it's kind of like what's happening in your freezer in case you've ever done it. So I thought I'd bring it down to home so you'd understand what it is. So it's not a very explosive or propulsive event. Just bear that in mind. So the second possibility is that there might be thrusters on a technological spacecraft. So how do you tell the difference? And this is what Avi Loeb is saying, okay? And he further went out that chemical rockets are propelled by exhaust velocities of 3 to 5 kilometers per second. That's about right, which is about 10 times larger than the maximum ejection speed of volatiles sublimated by sunlight from cometary surfaces. And he said that, ion thrusters would get up to 100 times more velocity than that, which is than these sublimation from pockets of ice, and that's about right. The ISP of ion thruster is indeed 10 times greater than that of a typical rocket engine. ISP is pound thrust per pound fuel consumed, and they get that through extra velocity. So, and then that's why I've had some interest in this Enzmann drive, because with that accelerate particles, the more acceleration you put them, you can get them up close to relativistic speed of light, or some fraction thereof, theoretically. Or something at least better than an ion thruster if you don't keep it in the going around and around and speeding up too long. But anyway, so that's more ISP, and more ISP, you're more efficient your fuel has been burned, the less fuel you require to do the job. Okay, so let's go back to this. He says, if it's a natural object, we know the temperature of the surface of the rock, given its distance from the sun, that gives characteristic speeds of any volatiles that get sublimated and ejected from those pockets of ice. For a natural comet, the outflow velocity of the jets is expected to be merely 0.4 kilometers per second, which I mentioned earlier, which is orders of an order of magnitude of speed of the gas, the distance from the sun, it's hard to read this, in order for the jets to extend the observed distance scale. So what he's saying is that the scale of the gas is 10 times at least more than it should be, given the acceleration, typical speed, velocity of sublimation process from the comet at 0.4 kilometers per second. So he said they should have been ejected for timescales of 3 months for the tail and 1 month for the anti-tail. Well, I gave you exact days, so he's kind of rounding it up a little bit. And for the most part, that's kind of hard to argue with. I did some checking that gas molecules are typically 0.3, which can be slower, up to 1 kilometer per second. And 1 kilometer per second is the fastest thing that I've seen at all in this. So it's just a little bit more than twice the speed of this, which should still give you over a month, almost a month time to create something that large as the tail we saw, which is indeed uh, uh, well, it should have taken 82 days, the normal 82, 83 days with a zero point 0.4 kilometers per second, but half that, 40 something. It should have been over a month, even if the fastest particles coming off of a comet in the order of some light gas molecules might get a kilometer per second. But fine dust goes 0.1 to zero point 0.6, which is in that 4 kilometers per second range, some of them a lot slower. And coarse dust coming off in the millimeter scale would it be expected, and this is the stuff you'd really see, at 0 0.1 kilometers per second. So a whole lot of this stuff is slower than that 0.4 kilometers per second. Okay, yeah, that's my little take on it. Just getting back into Avi Loeb here. He said, given that anti-tails are stopped at a distance of 1 million kilometers, well, they went just shy of 1 million kilometers, 0.95, which is practically 1 million kilometers. He said that implies the ram pressure exceeds that of solar wind out at that distance. Yeah, they're swimming upstream. The solar wind is flowing at a speed of about 400 kilometers per second, which is 1,000 times larger than the outflow speed from a natural comet. Since ram pressure scales at speed squared, just like drag speed squared, this means that the outermost surface area is squared for drag, excuse me. This means that the outermost mass density of the anti-tail is 1 million times bigger than that of the solar wind. A few proton masses per cubic centimeters. Uh, the outermost mass density of the jets give a mass flux of 2 million kilometers per second per million kilometers squared. Summing over these areas, an order of 10 million kilometers squared, yields a result of over 50 billion tons a month. Originally had this the upper limit of this, the lower limit of this comet mass at 33 billion tons. He says to just make the anti-tails, then it would have to put out something in the order of 50 billion tons a month. Now, it hasn't been thrusting for a month. And some earlier calculations he did suggested 5 billion tons, which we'll look at those in a minute. But it could be higher than that 5 billion tons, which it puts that forth a lot of ramifications in how big this thing is if it's natural. So he goes on, he says the mass is comparable to the minimum mass associated with 3I Atlas's 33 billion tons that calculated from the lack of non-gravitational acceleration in the months preceding October 25. Uh, so, they looked at it, prior to October 25, and they saw a mass ejection of something on the order of, two kangaroos, they said, per second. I think about 150 kilograms. And they didn't see any movement. So that set the lower limit. That should have thrusted a smaller comet to not have been moved around by that. It would have been at least 33 billion tons, at least. And like I said, that's the lower limit. Could have been more. Now it's looking like maybe more, maybe. Assuming a solid density of zero point 0.5 grams per cubic centimeter, this means that the diameter, which is pretty typical for a comet, low weight, low mass density, uh, this means the diameter of 3I Atlas must be bigger than 5 kilometers. Well, he goes on much bigger in a little bit. So if it is a natural comet and most of its nucleus survive perihelion, diameter of 3I Atlas should be 10 kilometers or larger. And we're going to talk about 20 kilometers in a minute. So, if, however, we consider the possibilities that the jets emanate from 3I Atlas are associated with technological thrusters, then the required mass can be 1 to 2 orders of magnitude smaller with human-made technologies. Now, that's 1 to 100 times less, maybe 1,000 times less with the higher velocity thrusters, or even better. Just depending on how much velocity you thrust at. Chemical rockets are propelled by an exhaust velocity of about 3 to 5 kilometers per second, which we touched on a minute ago, which is 10 times the maximum ejection speed of volatiles from sunlight. Yeah, we talked about that. Thrusters can reach speeds of 10 to 50 kilometers per second. Now you're talking. Furthermore, alien technology might employ thrusters for higher speeds, reducing the mass required to accomplish the mission. So by over 2 orders of magnitude. So yeah, so it'd be a smaller percentage of your spacecraft. So that's what I'm talking about. And something like an Innsman drive, which I've mentioned before. I may have to do a special on an Innsman drive one day. So I find that to be very fascinating. The sublimation of carbon dioxide, CO2, requires, now this is from an earlier post, 600 joules per gram. Nearly 5 times, well, he got this backwards, it's a fifth the sublimation rate of H2O at 2,835 joules per gram. Even Avi Loeb, astronomer, can make a mistake. He said 5 times, it's really a fifth. The Webb telescope spectrographic data, that's why you got an engineer here, guys, because I can see through these, I can catch the mistakes. Anyway, he said the telescope spectrographic data indicated that when 3I Atlas was 2.4 times farther from the sun than its perihelion distance, 87% of the mass of gas around it was CO2. In order to supply 5 billion tons of CO2 over the perihelion passage period of a month, now he's talking 50. Now he's talking 50 billion. See, this is an earlier passage. He is 10 times that because he's calculated those anti-tails. And that was just from the anti-tails, guys, not the tail. And the perihelion distance, the sun provided at the perihelion distance, the sun's providing about 700 joules per square meter per second, about a kilowatt per square meter. No, 700.7 kilowatts per square meter, 700 watts. So, this pretty much ties in. I think it's 770 watts. Anyway, this means that the absorbent area of 3I Atlas must be larger than 1,600 square kilometers. This is the area of a sphere with a diameter of 23 kilometers, 4 times larger than the maximum diameter of the 5.6 kilometers inferred by the 3I Atlas from the imaging data from Hubble telescope reported earlier. So the required diameter is 51 kilometers of water ice. So for water ice, 51 kilometers. So CO2, 23 kilometers. And whatever the case is, he's talking a really big object. Now, if it's that big, that's within resolving power, actually, of the high-res instrument on the Mars Reconnaissance Orbiter. Because it would have gotten the best image if it got an image of this than any instrument will in the entire passage of this 3I Atlas, simply because it was so close to Mars. It's going to be so far away from Earth that the best we can hope for with the James Webb telescope is like 42 kilometers and 50 some odd with the Hubble telescope. So NASA, knock knock. Hey, where's our images? You're waking up, NASA. You're going back to work. Why aren't you releasing these images? Oh yeah, we'll talk a little bit more about that a little bit. But anyway, so yeah, it's within resolving power. It still don't mean you wouldn't see fine structure on it, because when a pixel is 20 kilometers, or worse, that's mighty big. You haven't seen anything that is smaller than 20 kilometers, like windows, rocket motors, docks, or other spaceships. has been often reported by other YouTubers and God knows who else. Anyway, so basically, he says, Houston, we have a problem with that natural comet hypothesis. The required surface area of 3I Atlas provided to provide the inferred mass loss in the latest point post-perihelion image is at least 16 times larger than the upper limit derived from that Hubble image taken on the 21st of July in 2025. He says that when the Webb data was taken on 6th August 2025, the 3I Atlas had only lost, like I said, 150 kilograms per second. That was that 2 kangaroo per second number, right? That's some big kangaroos. Anyway, the mass loss at perihelion derived is on the order of 4 orders of magnitude larger, about 4 orders of magnitude. That is 10,000 times, in case you don't know what he's saying. That's 4 zeros. About 2 million kilograms per second. So you go from 150 to 2 million kilograms per second. This is a dramatic increase requiring a power law dependence of mass loss on distance from the sun when the power law index of 10.5 yeah, that's what he claims is the index, consistent with a rapid perihelion brightness of 3I Atlas. He says, was that dramatic loss of brightening of 3I Atlas at perihelion evidence that it disintegrated? Breaking up into fragments would further increase the surface area of the material. Now, there you go. That could be exactly what happened. Instead of having one object 10 kilometers in size, suddenly you got a whole bunch of objects and you got a lot more surface area. So break up into fragments will increase the surface area of the materials since the surface to mass ratio scales inversely with the characteristic radius of the fragments. An increase in the surface area by a minimum factor of 16 requires that 3I Atlas broke at least into 16 equal pieces and likely many more. That would mean that 3I Atlas exploded at perihelion and will witness the resultant fireworks. In other words, the latest example implies that 3I Atlas was decimated by heat from the sun if it was a natural comet. Decimated by heating when the heating is on the order of 700 joules, or, we're talking maybe a little over 0.7 kilowatts, or 700 to 770 watts per meter squared. That's like 100-watt light bulb shining on something across a square meter, making it explode. So, interesting. He said the tidal forces of the sun is expected to separate the fragments in the coming weeks, creating an appearance similar to that of a comet Shoemaker-Levy 9 in 1994 near Jupiter, which broke up into 21 principal parts. Now, what he's talking about there is when an object explodes, it's traveling and explodes like a bomb or a grenade, and all these fragments are coming off in different directions. They have additional energy imparted to them by the explosion, and they will start ripping apart. If it was an explosion, it might have just been a breakup. But in either case, the centroid or the summation of the velocities of all of these particles will still be essentially the same. They're still traveling along the same, even though their mass is spreading out, they're still traveling on the same center mass, the same momentum pretty much, although there's going to be some different momentum imparted by whatever explosive forces were put into it, but summed up, it should be about the same. So that's the interesting thing about it. So it will still travel in pretty much the same trajectory, just breaking apart. Now, if it's tidal forces that break it up, it would be more a train of objects that, like we saw with Comet Shoemaker-Levy 9. There was 21 objects all in a row, in a train. That's the way it broke up due to the tidal forces of the sun. And I'm thinking that, that big dust ball from the beginning of it may have been an indication of it having kind of sort of disintegrated, exploded, whatever you want to call it, but it may not have been an explosive explosion, just a breakup, a disintegration. Now, that typically happens when the comets are like very close to the sun. Some comets dive really close to the sun and they break up. But this thing was out almost to the orbit of Mars. It's strange that the tidal, but then maybe it's never been close to a star before, so maybe it's weaker and easier to break up. So it may have broke up just because, hey, this is first, passed by a star and it just couldn't handle it. Captain, she's breaking up. Captain, she can't handle it. But it could also be that maybe it's propulsive forces. Maybe it didn't break up. So the thing is, we shall see soon. We shall see soon. if this thing was broken up or not broken up, because on the 19th of December, it's going to be this closest pass. We're going to have every telescope aimed at this thing practically that can look at it. If it's broken up into major pieces, we should start to be able to discern something, even though we may not resolve each piece. There should be something that we can tell even out at that distance. So uh, that's just something to look at. So, going back to Loeb here, he says, however, if the upcoming observations should reveal that 3 Atlas was not decimated by the sun and maintain its integrity as a single body, then we have to consider something other than a natural comet. Separately from the required breakup of a natural comet, the large diameter of 3I Atlas highlights the first anomaly that Dr. Loeb pointed out for 3I Atlas, claiming it was really too big to have originated from interstellar space, at least on the, just by averages, although there may be some large objects in interstellar space. There's just not that much material there. And for this to originate there, it shouldn't have been like the third object we've seen. It should have been like farther down the scale. So that's his conclusions on that. So bear in mind that he's talking about this thing being perhaps uh, 23 to 50 kilometers in size, or the breakup really though explains a lot of it. But if it didn't break up, that's going to be kind of odd. That's going to be kind of odd. So how do we want to look at that? What do you think about it? Is this thing natural, or is it something else? Put your comments below. I'm still leaning toward a rock. But yeah, we'll have to see what this thing looks like on the 19th of December. We'll start getting some clues before then. And then even a little while after, but she'll start spreading apart, and we should have some clues. If we may not be able to resolve the exact nucleus, but if it breaks up into several different pieces, we should be able to resolve the commas around each piece, I would hope. That's what we could hope to see. We can't see stuff, smaller than 40 kilometers at that distance from even our best telescope, the James Webb Telescope. But it's too bad we don't have something closer there to look. Maybe next time. Anyway, space is interesting, my friends. It's getting crazy, crazier by the day. So with that, I'm going to say, I hope you enjoyed this video. Bang the bell, subscribe, bang the bell, click all. And above all, just keep looking up because space is interesting. Greg out.